Hi. Today also we are continuing the section prime and maximal ideals. Now, last class we have discussed about the definition of maximal ideal. Now we are moving to the definition of a prime ideal. An ideal n not equal to R in a commutative ring with unity. Must write commutative ring with unity is a prime ideal if AB belongs to n implies either A belongs to n or B belongs to n for AB belongs to for A comma B belongs to R. Okay, an ideal n not equal to R is a prime ideal if AB belongs to n implies either A belongs to n or B belongs to n for every A comma B belongs to R. If it satisfies this condition, then we call n is a prime ideal. Okay, now we are moving to one example of a prime ideal. If n is equal to set 0, then clearly this is a prime ideal in Z plus dot, because let AB belongs to n. AB belongs to n means n is set 0. That means AB equal to 0. In set of all integers, AB equal to 0 implies either A equal to 0 or B equal to 0. That means either A belongs to n or B belongs to n. So AB belongs to n implies either A belongs to n or B belongs to n. This implies n is a prime ideal. That means n equal to set 0 is a prime ideal of Z plus dot. Now next one, set 0 is a prime ideal in any integral domain. Let AB belongs to set 0 implies AB equal to 0. That implies either A equal to 0 or B equal to 0, because D is an integral domain. AB equal to 0 means integral domain means it has no 0 divisors. That means AB equal to 0 implies either A equal to 0 or B equal to 0. That means either A equal to set 0 or B equal to set 0. This implies 0 is a prime ideal in any integral domain. Now prove that set cross set 0 is a prime ideal of set cross set. So let AB belongs to, AB into CD belongs to set cross set, and this is equal to 0. Means what happens? Now what is n? N is set cross 0. That means n ordered pair n0 such that n belongs to set. Suppose AB CD belongs to n, product belongs to n means AB into CD means AC into BD belongs to n. This belongs to n. This AC BD belongs to n implies n is actually of the form set of all n0. So AC BD belongs to n means this BD must be equal to 0. So B and D are integers, therefore BD equal to 0 implies either B equal to 0 or D equal to 0. That means either AB belongs to n or CD belongs to n. If B equal to 0 means AB belongs to n. If D equal to 0 means CD belongs to n. That means AB into CD belongs to n implies either this condition holds or this condition. This implies set cross set 0 is a prime ideal. Now what about set cross Z over set cross set 0? This is isomorphic to set, which is an integral domain. Okay, therefore set cross set 0 is isomorphic to set, which is not a field. Therefore, set cross set 0 is not a maximal ideal in set cross set. We have a result. If R over M is a field, then M is a maximal ideal. Therefore, set cross set 0 is here. R over M is isomorphic to set. That is an integral domain. That is not a field. Therefore, set cross set 0 is not a maximal ideal in set cross set. Now moving to one theorem similar to theorem in theorem 1.15. What is theorem? Let R is a commutative ring with unity. N not equal to R be an ideal in R. Then R over N is an integral domain if and only if N is a prime ideal. Earlier it was R by M is a field if and only M is a maximal ideal. In the case of prime ideal, R over N is an integral domain if and only if N is a prime ideal. So suppose N is a prime ideal and we have to prove that R over N is an integral domain. Conversely, we have to prove R over N is an integral domain, then we have to prove N is a prime ideal. Suppose N is a prime ideal. That means for every a comma b belongs to R, a b belongs to n implies either a belongs to n or n b belongs to n. Since R is a commutative ring with unity, R over n is also a commutative ring with unity. To prove R over n is an integral domain, we have to prove xy equal to 0 in R over n implies xy equal to 0 in R over n implies x equal to 0 or y equal to 0. So xy belongs to R over n means what? Xy belongs to R over n such that xy equal to 0 in R over n means xy equal, what about 0 in R over n? 0 in R over n is n is. So xy equal to n. Now xy belongs to R over n means x is equal to, x belongs to R over n means x equal to some a plus n, y equal to b plus n. So xy equal to n implies, what is xy? A plus n into b plus n is equal to ab plus n. Okay, and this is equal to n. By definition, what we get is xy equal to 0 in R over n means xy equal to n. So xy equal to n means a plus b n equal to n. That means what we get? AB belongs to n. So AB belongs to n means what we get? AB belongs to n means n is a prime ideal implies AB belongs to n means either A belongs to n or B belongs to n. Either A belongs to n means A plus n equal to n, because if A belongs to n then A plus n equal to n, or B plus n equal to n, that means B belongs to n implies B plus n equal to n. Thus we get A plus n equal to n means x is equal to n, that means x is equal to 0 or y equal to 0 in R over n. Thus we get xy equal to 0 in R over n implies either x equal to 0 or y equal to 0. This implies R over n is an integral domain, because some AB equal to 0 implies either A equal to 0 or B equal to 0. Therefore R over n is an integral domain. Conversely, suppose that R over n is an integral domain, we have to prove that n is a prime ideal in R. So suppose AB belongs to n, then we have to prove that either A belongs to n or B belongs to n. A belongs to n means A plus B n equal to n. That is A plus n into B plus n is equal to n. That means this is equal to some xy equal to 0 in R over n. R over n is an integral domain. Xy equal to 0 in R over n means we have either x equal to 0 or y equal to 0. X equal to 0 in R over n means x equal to n. That is A plus n is equal to n or B plus n is equal to n. That means either A belongs to n or B belongs to n. Because A plus n is equal to n only if A belongs to n. Or B plus n is equal to n means B belongs to n. This implies n is a prime ideal, because we have assumed xy, we have assumed AB belongs to n, and we get either A belongs to n or B belongs to n. This implies n is a prime ideal. Now next is a corollary. Every maximal ideal in a commutative ring with unity is a prime ideal. Proof is very easy. Suppose M is a maximal ideal in R, then by previous result R over M is a field. Every field is an integral domain, therefore R over M is an integral domain. This implies M is a prime ideal. Okay, therefore every maximal ideal is a prime ideal. What about the converse? What about the converse? Converse need not be true. Okay, for a commutative ring with unity, what about the converse? Suppose M is a prime, here we get n equal to set 0 is a prime ideal in set, but this is not a maximal ideal, because maximal ideals of set are of the form P set. Okay. Now for a commutative ring with unity, we have an ideal M of R is maximal if and only if R over M is a field. An ideal N of R is prime. This is maximal, here prime, if and only if R over N is an integral domain. Now the last result, every maximal ideal of R is a prime ideal, but the converse is not true. Every prime ideal need not be a maximal ideal. For example, set cross set over set cross set 0. We have already proved set cross set 0 is a prime ideal of set cross set, but it is not a maximal ideal, because set cross set over set cross 0 is isomorphic to set. If this is a maximal ideal, then set must be a field, but here set is not a field, therefore set cross set 0 is not a maximal ideal, but it is a prime ideal. Similarly, prime ideals of set are set 0, Pz. Okay. Here this is not a maximal ideal. Okay. Now there is one theorem. If R is a ring with unity, then the map phi from Z to R defined by phi of n is equal to n dot 1 is a homomorphism. It is very easy. What we have to prove? We have to prove phi is a homomorphism. What we have to prove? Phi of m plus n is equal to m plus n. Phi of m plus phi of n. Also phi of m into n is equal to phi of m into phi of n. Here what happens? Phi of m plus n is equal to, by definition, m plus n into 1, and that's equal to m into 1 plus n into 1. That is phi of m plus phi of n. Okay. Now what about nm? N is same as 1 plus etc. plus 1 n times. M is same as 1 etc. n times. And this is equal to nm times, okay, 1. So n into 1 into m into 1 is equal to nm into 1. That means phi of mn is equal to nm into 1, which is equal to nm into 1 into m into 1. That is phi of n into phi of n. This implies phi is a homomorphism. Okay. Hope it is clear. Now moving to next, prime phi. Same theorem, fundamental homomorphism theorem. We have that phi from R to R dash is a ring homomorphism with the kernel n. Phi of R is a ring, and mu from R over n into phi of R defined by mu of x plus n is equal to phi of x is an isomorphism. If gamma from R to R over n is a homomorphism defined by gamma of x equal to x plus n for each x belongs to n, then phi of x equal to mu gamma of x. That is, R over n is isomorphic to phi of R. We have already discussed this result. Now let R be a ring with unity. If n into 1 not equal to 0, for every n belongs to Z plus, then R has of characteristic 0. We have already discussed this. If n into 1 equal to 0 for some n belongs to Z plus, then the smallest such integer is called, n is the characteristic of R. Now, this is also we have discussed. If R is a ring with unity and a characteristic n greater than 1, then R contains a subring isomorphic to Zn. If R is of characteristic 0, then R contains a subring isomorphic to Z. Once again, I am repeating. If R is a ring with unity with a characteristic n, and it is finite, then R contains a subring isomorphic to Zn. If R is of characteristic 0, then R contains a subring isomorphic to Z. Okay. Consider the map phi from Z to R. Phi of m is equal to m into 1. By theorem 1.21, phi is a homomorphism. We have already proved. And hence kernel of homomorphism must be an ideal in Z. Okay. Now what about the kernel? Note that the ideals in Z are of the form Sz for some S belongs to Z. So let n is equal to kernel phi, and that's equal to set of all x belongs to such that phi of x equal to 0. Okay, that is set of all x belongs to Z such that x into 1 equal to 0. And this is of the form some S set. Okay, because every ideal in Z are of the form this set. Okay, so by our assumption R is of characteristic n greater than 0, then n is the smallest positive integer such that n into 1 equal to 0. Therefore n belongs to n, and n belongs to what happens? N belongs to, okay, n belongs to S set, as n is the smallest positive integer such that n belongs to S set. What happens? N is equal to S, because in here in S set of all x belongs to Z such that phi of x equal to 0, clearly for every S this condition also holds. Okay, so in this case what we get? N is equal to S. N is equal to S means S Z is same as N Z. Therefore we have N is equal to N Z. By fundamental homomorphism theorem, Z over N Z is isomorphic to phi of Z, but Z over N Z is isomorphic to Zn. Okay, which implies Zn is isomorphic to phi of Z, which is a subring of R. R contains a subring isomorphic to Zn. Okay, so if R is of characteristic 0, same result. Okay, holds implies n is equal to z0 and we get z over n is isomorphic to phi of z, implies z over z0 is isomorphic to phi of z. Z over z, what is z over z0? Z. That means z is isomorphic to phi of z. That means R contains a subring isomorphic to z. Okay. Now, next result. Every field L containing an integral domain D contains the field of quotients of D. Already you have discussed this in your final year degree. Any two field of quotients of an integral domain are isomorphic. Now, last we have one result. Theorem. A field F is either of prime characteristic P and contains a subfield isomorphic to set P, or of characteristic 0 and contains a subfield isomorphic to Q. This is very important. Okay. If the characteristic of F is not 0, then F contains a subring isomorphic to Zn by previous result. Since F is a field, Zn is contained in N, implies N must be a prime number. Because if N is not a prime number, then Zn contains 0 devices. This implies F also contains 0 devices. That is a contradiction. This implies Zn is equal to Zp, which is a field. That means F contains a subfield isomorphic to Zp. Okay. Now suppose F is of characteristic 0, then by previous result F contains a subring isomorphic to Z. Then by result 2.4, this every field L containing an integral domain D contains the field of quotients of D. That means then F must contain field of quotients of this subring, and field of quotients of Z must be is isomorphic to Q. Field of quotients of Z is isomorphic to Q. You have already discussed in your degree final year. Okay. Thus, every field contains either a subfield isomorphic to set P for some prime P and or a subfield isomorphic to Q. And these fields Q and set P are called prime fields. These fields set P and Q are called prime fields. Okay, that's all for